All right, so this is Math 150 Calc 3. This is lecture 9, and today we're finally going to start, doing actually multivariable calculus. After spending, quite a lot of time just doing, preliminaries and background material, we can now finally start to do the real subject. And again, it's a little bit annoying to spend so much time on preliminaries, but you really need to learn the notation. So today we're going to talk a little bit about limits. We're going to talk about 3 different definitions of a derivative in one variable, and then we're going to talk about partial derivatives. I think the video does the, you can learn partial differentiation in under 1 minute. Was that in the video? Yeah. It really doesn't take that long to learn how to do a partial derivative if you know how to do derivatives. What takes a long time and is typically not done in the first is all the rigorous theorems. When is a function differentiable? It turns out it's not enough for the partial derivatives to exist. All right, so the basics of everything is we need to understand limits. And the idea is we say the limit as x approaches a of f of x is f of a if the distance between f of x minus f of a goes to 0 as x gets closer and closer to a. And so this would be the definition of continuity. So our function is continuous if its value at a point is the same as the limit as we get closer and closer. So for example, if I give you a plot of a function, there's one point where this function would not be continuous. And it's at that point where I have a split definition. So over here, we would have a discontinuity. Okay. So how many of you have seen epsilon delta proofs? This is sometimes done in Calc 1, Calc 2. It's usually, with partial fractions, the most hated part of the course. It's just going through and doing everything with extreme rigor to prove what's going on. And so for the most part, we're not going to really worry about that. If you take real analysis, then they will go into excruciating detail of just justifying what your intuition is saying in terms of everything is converging and everything is nice. So let's think about limits. So imagine you live in a one-dimensional world, and here's your point A. Essentially, how many different ways can I approach the point A? 2, and what are the 2 ways? From the left and from the right. So, somebody was commenting to me yesterday, well, maybe what you could do is you could overshoot and come back and whatnot. But if you overshoot and then you're traveling in the other direction, think of that as really canceling out and you don't really need to look at it. So there's really only one way to approach a point. Well, I guess 2, from the left and from the right. So if the limit exists in one dimension, I'm really only talking about 2 paths. Is 2 a large number? Not really. How many people have seen the Karate Kid series? Who knows the secret of Miyagi Karate? This was in the Karate Kid 2. The movies, I think, get exponentially worse as you go further and further. Although from the few episodes I've seen of the new version on, is it Netflix or YouTube Red? What I've seen is actually pretty good of the new remake, or I guess the, so many decades later. So instead of doing the secret of Miyagi Karate, I will do the secret of multivariable calculus. If you can understand the following limit, you understand everything. So here's my point A. And can somebody give me a way to approach A? How could I approach this point? Give me a path that gets me to the point A. 2 dimensions. From the bottom. What else? From the top. These are going to be the df dy's, the partial derivative of f with respect to y. Give me another way to approach. From the left and from the right. And in a shock, These would be the df dx's. What about another way to approach? So I could approach diagonal, and in fact, there's infinitely many diagonals I could approach along, right? I could approach along a parabola. I could have some fun. I could approach along some kind of maybe logarithmic spiral. Or if I really wanted to get crazy, so long as the radius is getting smaller and smaller and smaller, I could do something like that. So I want the limit to exist along all paths. And so it's not enough to just add what's going on along the standard x-axis, y-axis, stuff like that. I have to be able to do it along every possible path. And so in one dimension, to say the limit exists is not really saying that much. In two dimensions, as soon as I say the limit exists, I have given you a tremendous amount of information. If I ask you to exhaustively check all the possibilities in one dimension, is this a big deal? If I ask you to check exhaustively all the possibilities in two dimensions, this is the rest of your life and the life of all of your descendants and all their descendants, and you will never get there. We need a better way. And this is where the advanced theory comes from. It says, hey, if the partial derivatives exist, if the limits exist along special paths, and things are not too crazy, then it will be differentiable, and the limit will be independent of the path. So if you only need to check along certain paths, then you will get the answer along every path. Right. So to give some examples, so what I did is I plotted the function x squared y squared to the 1/3. And if you look at it, I also used the contour plots that we were talking about last time to try to get a sense of what's going on. Is the function x squared y squared to the 1/3 or just xy to the 2/3? This is defined for all x and y. When I take the cube root of a number, if the number is positive, its cube root is positive. If the number is negative, its cube root is negative. So everything is okay here. If you look at it though, I gotta stop the share before I go to the Mathematica. And so if I go to Mathematica, I've plotted it over here. Here is my object. And again, I can turn it around and just try to look at it. You're looking straight down, looking from the bottom. You can see there's some kind of strange difference in behavior. Where are we getting that strange difference in behavior? So where are the trouble points? It's actually pretty nice everywhere except where. Yeah, along the x and y axes, that's where we're having some trouble. Everywhere else, it's okay. So what we want to do is we want to try to understand how do we take derivatives of stuff like this. So let's review Calc 1. So we need the definition of the derivative at, say, x equals a. And there's three ways to write it. One, it's the limit as x goes to a of f of x minus f of a over x minus a. Two is the limit as h goes to 0 of f of a plus h minus f of a over h. So hopefully you've seen both of these. Which one have you used the most? The first one. So you normally do x goes to a. I actually like the second one because then my limit is always the limit going to 0. And I'm looking at the slight change from that. And I'm evaluating, but both of them are actually nice. There is another definition. And the last one is the limit as h goes to 0 of f of a plus h minus f of a minus f prime of a x minus a actually, let me rewrite this slightly. I'm going to change it so slightly. Let me do it this way. The limit as x goes to a of f of x minus f of a minus f prime of a x minus a over x minus a. With a little bit of work, you see that I can represent this as the limit as x goes to a of f of x minus f of a over x minus a minus f prime of a. Well, if the function is differentiable, f of x minus f of a over x minus a, that's supposed to just go to f prime of a. And so if I'm subtracting off f prime of a, what should this limit equal? 0. So this is another way of writing what it means for a function to be differentiable, is that this expression, f of x minus f of a minus f prime of a over x minus a over x minus a equals 0. All right, so why is this an interesting thing to study? Let's reset it. So here's the expression. So when you look at this, we have the quantity f of a plus f prime of a x minus a. Does that remind you of anything? Yeah, point slope form for what? So that's basically like the point slope right here. So here's my point A, f of a, and the slope is f prime of a. This is the tangent line. So what we're saying in one dimension, the function is differentiable if the difference between f of x and the tangent line approximation at x is so small, it goes to 0 when we divide by x minus a. So you should view this as, this is over here, this is the elapsed time. We started at a, we ended at x. This is how much time has passed. This is the speed at a, and this is our start location. So what we're saying is that where we are at time x is well approximated by where we started, plus a little bit of a boost. How much of a boost? The instantaneous speed times how much time has elapsed. Well, if we go over a very small period of time, we expect that it's going to be a pretty good approximation, just because the function doesn't change that much over a small scale. What makes this have real content is we divide by x minus a. And x minus a is extremely small. So think of x minus a as 1 over quadrillion. So we're saying the error in the numerator is so small that even when you divide it by 1 over quadrillion, it's still going to be small. Okay. So if we were missing by, say, 10 to the negative 4, but we're dividing by 10 to the negative 8, what's 10 to the negative 4 divided by 10 to the negative 8? 10 to the 4, which is huge. So it's not enough to say the numerator is small. The numerator is going to be small if the function is continuous. Just going to be forced to be that way. The real content is it's so small that even when we divide by x minus a, we get something that is tending to 0. And again, there are three different definitions of the derivative of a function in one variable. Normally, when we compute things using 1 or 2. We often use the f of a plus h minus f of a over h. So for example, if I had f of x is x squared, I would get f prime of x is the limit as h goes to 0, x plus h squared minus x squared over h. This is the limit as h goes to 0, x squared plus 2xh plus h squared minus x squared over h. This is the limit as h goes to 0. The x squareds cancel. I get 2xh plus h squared over h. This is the limit as h goes to 0 of 2x plus h. And as h goes to 0, what does 2x plus h go to? 2x. And here is our derivative. The derivative of x squared is just 2x. And there is the nice proof you're using the second one. I could try to use the third and say, hey, I know I have a guess that maybe my derivative is 2x. Let me try putting in that for the third one and show that the limit is 0. So there's a real difference sometimes between what do you use to compute and what do you use when you are actually just trying to write down a theoretical statement. And we'll see this when we get to directional derivatives. There's the definition of the directional derivative, which you would never use in practice to compute something. And then there is the reformulation. How many people here have taken statistics? So if you've taken statistics, you might know that there's different ways to write down the standard deviation of the variance. And so sometimes you have the theoretical one, where you might look at all the differences, and then you might have, it's the expected value of x squared minus the square of the expected value, which might be easier for some calculations rather than redoing some of the sums. So sometimes, depending on how you have information, one way of attacking the problem is going to be easier than another. So for us, in one dimension, we want the tangent line to do a really good job of approximating the function. And if the tangent line does a good job of approximating the function, then we say that the function is differentiable and its derivative is f prime. What do you think we would do in multivariable calculus? A function of two variables, f of x, y. What do you think the tangent line becomes? Tangent plane. And so what would be the tangent plane? It would have to start off with f out of the point AB. And then we have two different directions. We could be going in the x direction, or we could be going in the y direction. So if we go in the x direction, I'm going to write it as df dx at AB. So this is the partial derivative of f 2x keeping y fixed. So this is just looking along we keep y fixed, only we got it as a function of x. And then what would we have to multiply this by? So we have the point AB, we have the point xy. What would we have to multiply this by? Yeah, by x minus a. And now we have the other direction. So what would the other direction be? So df.
Yeah. Over dy.
Good. Yeah, times y minus b. And so this would be the tangent plane. And then we'll say a function is differentiable if when you subtract the tangent plane, it goes to 0. So say f is differentiable at AB if the limit as xy goes to AB, I gotta be a little bit careful here. We'll have f of xy minus f of AB minus df dx at AB x minus a minus df dy at AB y minus b over what? Well, if you look at the distance from xy to AB, what's the distance from xy to AB? Yeah. So I can't just write xy minus AB because that's a vector. I can't divide by a vector. I have to divide by the length of the vector. And this is supposed to equal 0. So this is the length, and it's x minus a squared plus y minus b squared square root. So this is the rigorous definition of what it means for a function of two variables to be differentiable. What's wonderful about this is that if the tangent plane is doing a great job approximating, it's not going to matter which way we approach. And so to just define things rigorously, df dx, the special d at the point AB, this means the limit as h goes to 0 of f of a plus h b minus f of ab over h. And similarly, df dy at ab is the limit as h goes to 0 of f of a b plus h minus f of ab over h. And so these are the partial derivatives. And the idea is that if we understand what's going on with the partial derivatives, if the function is nice, then we understand what's going on in general. We just have to understand in these special directions. This leads to some nice notation. We do f sub x of AB and f sub y of AB to denote, hey, I took the derivative with respect to x, and then I took the derivative with respect to y. And then later, once you take one derivative, what can you do? So if you can differentiate once, what could you do? Again and again and again. So I could differentiate with respect to x and then y, or with respect to y and then x. Does it matter which order I differentiate? So if I give you fxy, is this d by dy of df dx or d by dx of df dy? Which is it? Doesn't matter. Same if f is nice. So almost every function we look at is going to be such that it doesn't matter which order you differentiate. If you differentiate with respect to x and then y, that's the same as differentiating with respect to y and then x. But there is a canonical choice of which is which. We'll get to that later. So the definition of the partial derivative is not too bad. It's hold one variable fixed. If you have more than two variables, hold every variable but one fixed and just vary the other. Let's do an example too. Let's say I give you f of xy is x cubed y squared plus cosine of sine of y. What is df dx? So treating y as a constant, what would df dx be? So y is a constant. What is df dx? Yes. 3x squared y squared. This has no x dependence. We know the derivative of x cubed with respect to x is equal to 3x squared. Y squared is just a constant. What would d squared f dx squared be? The derivative of the derivative of f with respect to x, with respect to x. 6x y squared. Let's do one more. What's df dz? So what would df dz? 0. Right? Why didn't I ask for you to give me df dy? It's a little bit more work. I have to use a chain rule. Right? But df dz, that's actually pretty easy to do. Why is df dz 0? We're treating everything else as a constant, and there's no z dependence. So no matter what value of z you give me, I get the same value back. So really, if I wanted to do this, this is bad notation. I should really write this then not as f of x, y. How should I write this? F of x, y, z. So I should really write it as f of x, y, z to indicate that z is in play, that z is one of the variables. And you may have something where it doesn't depend on that variable. Okay, so finding partial derivatives is not too bad. If we go just along the x-axis or just along the y-axis. The real challenge is when we have these strange functions. And so for example, let's consider f of xy equals, say, xy to the 2/3. Okay. And we want to try to calculate the derivative. As long as x and y stay away from 0, this function is going to be pretty easy to look at. The real problem is when one of them is 0. And it's going to then depend on how we approach this. So for instance, what is f of 0, comma y for any value of y? It's just going to be 0. And f of x, comma 0 for any value of x is going to just be 0. So let's take y to be x to be 1/4. Let's take x goes to 0 plus. This means from above to positive values. I'm going to let g of x be f of x, x to the 1/4. So I'm coming along this curve, y equals x to the 1/4. What's my function going to be? It's going to be x times x to the 1/4 to the 2/3. So this is x to the 5/4 to the 2/3. So this is going to be x to the 5/6. Right? What if I try to take the derivative of x to the 5/6? What happens? As x goes to 0, what's going to happen to the derivative of x to the 5/6? So, what's the derivative of x to the 5/6? So as x goes to 0, this blows up. So if we approach the origin along this path, and we start computing what goes on, it's going to blow up. Let's try now y equals x. And let's let, we'll do c right as the curve. It's going to be f of x, which is going to be x times x to the 2/3. This is x to the 4/3. So what's c prime of x going to be? So what would c prime of x? Yes. 4/3 x to the 1/3. It's well defined. So along this path, everything is okay. Let's expand out about this a little bit more. Let's look at f of xy is xy to the 2/3. Let's look at df d at 0, 0. So this is the limit as h goes to 0 of f of 0 plus h 0 minus f of 0, 0 over h. What is f of 0 plus h comma 0 equal to? It's equal to 0. And what's f of 0, 0 equal to? So when x and y both equal 0, what is f of xy going to be? Also 0. So we have 0 over h, which is just 0. Similarly, df dy at 0, 0 equals 0. So the partial derivatives exist. So partial derivatives exist, but the function is not differentiable. And this just shows you the danger of looking at problems like this.
Why?
Yes.
Why are you saying it's not differentiable based on this?
So we should basically be able to get the same limit no matter how we approach. No matter what path we take. So again, go back to the Miyagi karate. No matter what path I take, I want to see the same behavior. We've just seen that as we approach in different ways, we can get different answers. The tangent plane is not going to be a good approximation everywhere. If we try to use the tangent plane, we've got df dx at 0, 0, 0. We have df dy at 0, 0, 0. So we would just say we should just approximate our function by 0. And that's not a good approximation. So it's always a question as to how much detail does one get into in a first class in the subject. And so this is not an advanced theoretical upper level math class. We fortunately have advanced upper level theoretical math classes. So if you like stuff like this, you will be able to see in much greater detail. What I want to do is I want to do just enough so that you know there and you don't just use theorems blindly, that you realize I have to be a little careful. It's not enough for my function to be differentiable. And so there's a theorem that says if the partial derivatives exist and are continuous, then the function is differentiable. And so partial derivatives are not continuous. And that is the big problem. So, yes. Yes. Because h is not 0. So remember, in our definition, the limit as h goes to 0. H is never 0. H gets as close to 0 as you want without ever actually being 0, because we're not allowed to divide by 0. So the whole point in calculus is you're looking at the change in the numerator over the change in the denominator. So if you're thinking of your variable as time, you can think about how far have we traveled in a very small amount of time. And when you look at it like that, the small amount of time is never 0. So h is not allowed to be 0. So if the partials exist and are continuous, then f is differentiable. So this is one of the big theorems. We're not going to prove that, but we're at least going to be aware of its existence. So most of the time, we're going to be looking at functions that are nice, and it's not going to be too hard to show that they are continuous.
So how are the ones on the left page not?
Well, we saw that we can get different answers depending on how we approach. So let's talk a little bit about different paths. Let's do some paths. So let's consider find the limit as xy goes to 0, 0. Let's say x squared plus y squared over x to the 4th plus y to the 4th. So the limit exists. So if the limit exists, what must be true? Well, there's no derivatives right now. I'm just asking, what does it mean for this limit to exist as xy goes to 0, 0? So for the limit to exist as xy goes to 0, 0, what must be true?
Not undefined.
Okay, so it's more than just not undefined. For the limit to exist, what is the definition for a limit to exist? I've got my point 0, 0. And what must I observe as I approach 0, 0? Right, so I could come in along the line, I could come in along the parabola, I could spiral in, no matter what path I take. So if the limit exists, then every path you take has to give the same answer. So if you want to prove the limit exists by checking every possible path, you will spend the rest of your life, unless you can find a way to check essentially all of them simultaneously. However, if you want to prove the limit doesn't exist, how can you prove the limit doesn't exist? So find any two that are different. So can somebody give me one path that I could try checking? What's a good path to take? Good, so take along the x-axis, so try y equals 0, and now we have the limit as x goes to 0 of x squared over x to the 4th, which is the limit as x goes to 0 of 1 over x squared. What does that equal? Blows up. So limit does not exist. I didn't even have to check two paths for this one. Just one path was enough to show the limit doesn't exist. Okay. So now let's look at the limit as xy goes to 0, 0 of x squared minus y squared over x squared plus y squared. So what's the first path to take? So good, so we could take x equals 0. So this is the y-axis path. And we get the limit as y goes to 0 of negative y squared over y squared. That's the limit of -1, which is just -1. What's another path? The x-axis. And along the x-axis, now we have y equals 0. So we get the limit as x goes to 0 of x squared over x squared. This is the limit as x goes to 0 of 1, which is 1. So limit does not exist. So for this one, we can see the limit doesn't exist. let's do a more interesting one. So let's do now the limit as xy goes to 0, 0 of x squared plus 17. Let's do x to the fourth. X to the fourth plus 17 x squared y squared plus y to the fourth over x squared plus y squared. What's a good path to take? So if we do x-axis, this is y equals 0, we would get the limit as x goes to 0 of x to the fourth over x squared, which is the limit as x goes to 0 of x squared, which is just 0. And this is also true for the y-axis. You would also get 0. What's the easiest way to see that it's also true for the y-axis? You could, of course, do the calculation, but I claim you don't have to do the calculation if you appeal to a certain result. It's symmetric. It's symmetric in x and y. So at this point, do you believe that it might be, that it might have a limit of 0? Or is 2 such a small number relative to infinity that you'd like a little bit more? So what's another path we could try? I'm sorry? Sorry? I can't hear you. There's no z in here, so we just have x and y. So I need another path. I need y as a function of x or x as a function of y. We just did x equals 0, we did y equals 0. We could do y equals x, or more generally, let's try y equals mx, because then I can check infinitely many lines at once. And that's much better than just doing it one at a time. So then I would have the limit as x goes to 0 of x to the fourth plus 17 m squared x to the fourth plus m squared x to the fourth, right? All divided by x squared plus m squared x squared. So this is the limit as x goes to 0. Oh, I've got an x to the fourth over x squared, right? And then everything else in the numerator is going to be 1 plus 17m squared plus, oh, this should be m to the fourth over here, sorry, plus m to the fourth over 1 plus m squared. What is this limit equal as x goes to 0? It just equals 0. So along every line, we get 0. What could we try after trying all the lines? So we could try parabola. We could try, y equals mx squared, also 0. Oops. Okay. So at this point, do you believe that it might have a limit of 0? It's not a proof yet. But we're now getting a little bit more evidence. So what we're going to do now is we're going to do what's called the polar trick. So polar trick for limits. Let's let x equal r cosine theta, y equal r sine theta. As xy goes to 0, 0, what does this mean in terms of r and theta? So if x and y is getting closer and closer to 0, what must be true about r? What must be true about theta? Why? Okay, so we know r is the square root of x squared plus y squared. If x is going to 0 and y is going to 0, then the sum of their squares is going to 0, so their square root of the sum of the squares is going to 0. So we know r goes to 0. You are welcome to revise your answer.
It depends on the rate at which x is changing.
So theta is completely free. Theta can do whatever the hell it wants. All I know is that if x and y go into 0, r goes to 0. Theta can do anything. And so now, this is the same as, let's look at the limit. As r goes to 0, theta is free. X to the fourth is going to become r to the fourth cosine to the fourth theta plus 17 cosine squared theta sine squared theta plus r to the, sorry, there's an r to the fourth here, plus r to the fourth sine to the fourth theta over r squared. So this is the same as the limit as r goes to 0, theta is free. We'll just have r squared times cosine to the fourth theta plus 17 cosine squared theta sine squared theta plus sine to the fourth theta. Because the numerator, every term has an r to the fourth, the denominator has an r squared. So what's this limit going to be? It's just going to be 0. We've now checked infinitely many paths. And so notice theta is just along for the ride. And so by checking just as r goes to 0, we are able to prove that the limit really does exist. Let's go back and let's revisit a problem we did a little while ago. So we're going to revisit the limit as xy goes to 0, 0 of x squared minus y squared over x squared plus y squared. This is the same as the limit as r goes to 0, theta is free of r squared cosine squared theta minus r squared sine squared theta over r squared, which is the limit as r goes to 0, theta is free. The r squareds cancel, and we get cosine squared theta minus sine squared theta. And now we see the limit depends on what theta does. So depending on how theta goes, on how theta varies, we get different things. If we take theta equals 0, we get 1. If we take theta equals pi halves, we get negative 1. So theta equals 0 gives 1, theta equals pi halves gives negative 1. What's another good choice for theta? We did 0, we did pi halves. Could do pi. I would do something else. We did 0 and we did pi halves. Pi over 4. So we do theta equals pi over 4, then we'll get 0. And so we see that depending on how we choose to approach, we can get very different answers. Okay. So this is, a lot of theoretical material here. The real big concern is, when does the limit exist? If the function is nice, it's a simple polynomial, it's not too bad to show that the limit exists. If I give you something more and more complicated, a really good trick is to replace x with r cosine theta, y with r sine theta. But what if we were not in 2 dimensions? What if we were in 3 dimensions? What would we use? Spherical. And if we were in 4 dimensions, you would use the generalization of spherical in 4 dimensions. Right? And there's a way to just do arguments like this. For the most part, we're going to be more concerned with just actually doing the computations. And so to do the computations, it's 1 minute to learn how to take a partial derivative. It's just take the other derivatives and just have the other variables along for the ride. So if I have the derivative with respect to, so when you were taking Calc 1, did they ever say things like take the derivative with respect to x? It's like, well, that's the only variable in play. You know, why are you saying take the derivative with respect to X? Is this in homage to the great Rodney Dangerfield, the comedian who gets no respect? No, it's because they know what's coming. They know later there's going to be multiple variables. And so if you start getting in the habit of saying with respect to X, when you have more variables in play, it's going to be clear what you're differentiating with respect to. All right, this is a good place to stop. If anybody is interested